All right. Welcome back to the live sessions of the course Viscous Fluid Flow. So today we begin with week 5. So quickly, we will basically recapitulate what we learned in the previous week, that is week 4's contents, and then we will begin by understanding what we shall do in this week's session. So if we quickly go through what we learned in 1 second. Yeah. What we learned in the previous week. So we basically looked at the special case uh, of a fluid mechanics problem where basically the two cylinders. So we were essentially solving the Navier-Stokes problem involved in the process of an extrusion process where basically the two cylinders were rotating with some given angular velocity. And also there was an axial pressure gradient, which is basically used to move the fluid out of the space. But what we did is we looked into a special case where basically the axial pressure gradient was said to be equals to 0. And then what we looked at is that we looked at the condition where the angular velocities of the cylinder were basically known, and they were of the same order of magnitude, or in fact they were of the same magnitude. Or it's the case when omega 1 is basically equal to omega 2. So in that case, using the simplification that there is no axial pressure gradient, by substituting that in the u theta expression of velocity, we found out that the velocity was basically omega times r. That is, the theta direction velocity is basically omega. It's just the product of omega and r. Then what we did is we applied the Navier-Stokes equation in the r direction, and we saw that the radial pressure gradient, which is basically the del P by del R term, is essentially balanced by the centripetal force, or is essentially balanced by the centrifugal force. And then what we did is we tried to understand how this balancing act takes place, and we saw the specialized case of a rigid body motion. As you can see, so basically this very expression suggests that there is now a rigid body rotation. And then what we looked upon is we saw basically the direction of this del P by del R and the centrifugal force. And then we saw that why this is known as a rigid body motion or a rigid body rotation is the very fact that tau r theta, which is basically the viscous shear stress in the r theta plane, basically goes to 0. All right, so this is something that we saw, and then we began by understanding an important aspect of solving problems in fluid mechanics, especially, which is basically the scaling analysis and choosing characteristic scales based on the various variables that we commonly witness. For instance, we saw the characteristic velocity scale, we saw the characteristic length scale of a problem, how we choose the characteristic scale for viscous stresses, and then we saw then we basically define the characteristic time. Then if you remember, we said that if if the like so the idea is that if we have defined a particular time for a particular problem in which there is an appreciable change in the velocity, then we basically have our own inherent time. For instance, if the bird flaps its wings with omega, then the characteristic time scale is basically omega inverse. However, in many instances, we do not directly encounter the given time scale trivially. So then we basically look for TC, which is basically the characteristic time scale, by matching certain quantities. We saw the advection time scale, and basically we also saw the diffusion time scale. So these are again obtained by so if we want to get the diffusion time scale, we said that the order of magnitude of this term in the Navier-Stokes equation is basically equal to the order of magnitude of this term, and so on in a similar way we get the advection time scale as well. Then finally, we saw that what essentially will be the scale for pressure, and a very important conclusion that could be drawn from this pressure analysis is that pressure can either scale as a viscous term or it can scale as an advection term, and the Reynolds number typically decides by which scale do we need to scale the pressure term. Okay, so for instance, if Reynolds number is very less, or if we are in the viscous regime, then pressure scales as the viscous scale, which is the dynamic viscosity times the characteristic velocity divided by the characteristic length. In the other way, if the Reynolds number is large, pressure will basically scale as the advection term, which is basically rho times the squared of the characteristic velocity. And then these are the two conclusions, as I have already said, that the way in which pressure scales depends on the Reynolds number of the problem. So it's just that we cannot define an exact scale of pressure universally. So it depends on what problem we are basically solving for. All right. So this is something that we learned in the last week. But I said that although we saw what scaling analysis means, we have not applied that. We have not basically applied that in any problems yet. So in this week, we will essentially solve a very important problem. These kind of problems, I think we have solved in this week's lecture series, or I think this to the previous week's lecture series. The problem is very similar to the one that is been taught in the week's contents, but we will solve that problem by using the knowledge of characteristic scale, and more precisely, we will solve that non-dimensionally. So we will see that the beauty of a non-dimensional problem is that we don't need to care. We don't need to care about physical quantities like the viscosity, the density, or so on and so forth. All we will do is we'll just non-dimensionalize the pertinent variables using the appropriate characteristic scales, and we'll get a very neat and clean non-dimensional expression. And our aim is to just solve that non-dimensional expression with some non-dimensional number that obviously it will appear in the analysis. So this is something that we will see today, and hopefully we will acknowledge the importance of using characteristic scales and characteristic variables, and more importantly the idea of non-dimensionalizing a particular problem. So, in order to learn that, we will solve this problem today, which is basically the time periodic pressure driven flow in a cylindrical pipe. So, I think this so I think you have learned the Stokes first problem in the weekends. I mean in the week's class where you so what was the Stokes first problem? Can you tell me what is can can you recollect what was Stokes first and the second problem? Yeah, go ahead.
A plate at rest is suddenly brought to
Exactly.
motion.
So
Stokes first
so
problem.
it was Stokes first problem or the second problem? Yeah, you are right. You are right. But there were two problems of Stokes basically. So I think the one that you said that there is a plate which was initially fixed and there is a chunk of fluid that is above it, and the plate is then suddenly so at time t equal to 0 plus we assign a particular velocity to the plate. So can you tell me this? So you are right, but is it the Stokes second problem or it's the Stokes first problem? Or both are essentially the same?
First problem.
Yeah, exactly, exactly. So can you tell me what was Stokes second problem? If you so or like is so yeah.
Oscillate.
Yeah, exactly, exactly. Exactly, you are right. So the Stokes second problem was basically similar to the first problem. The only difference is that in the first problem we set the plate in motion. Okay. But in the second problem, instead of just assigning a particular velocity in a particular direction, we oscillate. So we assign oscillating velocity to the plate. So that's the physical idea. But here I will ask a very important question that do you remember we essentially solve the Stokes first problem and the second problem in two different ways. Can you recollect how did we solve the Stokes first problem? What is the method by which we solve the Stokes first problem? Do you recollect something which is called a similarity variable?
Similarity.
Yes. But did you use similarity variable in the Stokes second problem? Can you recollect?
Second problem, we assume
Uh, I could not hear you actually. Can you repeat?
second problem we assumed one form of solution.
Exactly, exactly. So you are right. So in Stokes' first problem, we solved that using a similarity variable, but in Stokes' second problem, we assume the form of the solution that it is some real part of some function of r times some function of time. Is it? So that's something that we did, right?
Yeah.
Yeah. So can you tell me why did we solve these two differently? Why can't we use the approach of the Stokes second problem into the first problem or vice versa? So what essentially was missing in the Stokes first problem that was available in the Stokes second problem or like the other way around? That is the question that I want to put forward. Can you tell me by like you can think about and you can tell me that's not so trivial question. Oops. So I'll give you a hint. I'll give you a hint. So this is not a part of this exercise, but this will help us, or this will help us, so this will enable us to develop our understanding how to choose an approach for a particular problem if we are given like two similar cases but the resulting solution may be different. Okay, so I'll give you a hint. So in Stokes' first problem, so let's look at the Stokes first and the second problem. Okay, so in Stokes' first problem, I'll also define the axis here basically. So the red colored line is the plate. Okay, the red colored line is the plate. Pardon my drawing. So this axis is not looking good. One second. So yeah, so it is something like this, something like this. Okay. So I'll just consider this as my y direction in both the cases. This is my y direction. This is my x direction. And of course, this is my x direction. So in the Stokes first problem, I'll just write it ST first. What we saw is the plate is given a velocity up at some time t equal to 0 plus, and it is just some number. Let's say it is some alpha, and this alpha is known. However, in Stokes' second problem, I'll write it as ST second. What we saw is the velocity of the plate at time t equal to 0 plus. Of course, the plate was initially stationary. So the initial condition was that at t equal to 0, the plate is stationary. The plate only acquires a velocity at t equal to some positive, so at t greater than 0. Okay, some positive non-zero values of time. Okay, which is close to 0, of course. However, in second problem, we said that the plate, instead of just moving with a constant velocity, it oscillates back and forth about, let's say, the axis yx with some, let's say it's some alpha star cos of omega times t, right? So this is essentially the main difference that lies in the Stokes first and second problem. Now, as you have rightly pointed out, we used similarity variable here. Maybe you have defined some similarity variable eta or whatever you use. The symbol is immaterial. However, in the Stokes second problem, we use something. So you can say we use the variable separation technique basically. The idea is that you approximate a form of the solution, that your velocity, that the fluid velocity will be some function of r times some function of time. Now my question is, why the approaches in these two problems are different? That is the question. Because the problem looks similar, right? The only difference is that in one case the velocity is known, in the other case the velocity is known, but it now oscillates. So it's not a simple question, I
Boundary
would say.
condition.
Boundary condition.
Boundary.
Okay, okay, that also I'll simplify to you. So let's think about this. So let's think about the boundary conditions. Right, that's an important aspect you are bringing about. But let's think about the boundary condition. So in Stokes' first problem, so what's the boundary condition here? The boundary condition at y equal to 0 is basically the fluid velocity. Let's say so the fluid velocity at y equal to 0, okay, for all time is basically the plate velocity, right? It's just up. Is this correct? This is correct, right?
Yeah.
And
No,
yeah, and what's the velocity when y tends to infinity? What's u when y
zero.
tends 0? Okay, fine. Now let's look at the second problem. So what's the boundary condition here? So boundary condition is same, right? So the fluid velocity at all times when y becomes equals to 0 is basically what? It's just up, right? Only the form of up is different. That earlier up was just alpha. This time it is just alpha star time cos omega t. Okay, right?
It's a periodic.
Yeah, exactly. So you are coming to the answer. So your answer is right, but at the exact point of your answers is not exactly what I want to hear. But conceptually you have given the right answer. See, in the Stokes first problem. So now at least we appreciate that the boundary conditions are also similar, right? Except that we are looking here into a periodic boundary condition. See, the difference lies in this, that listen to this very carefully. In the Stokes first problem, we did not have a defined time scale. Okay, do we have a defined time scale for this problem? Can you tell me that? Yes, did we have a defined time
No,
scale?
no.
No, right? However, in the Stokes second problem, we had a defined time scale. So can you tell me what will be the characteristic time scale of this problem? TC?
1 by omega.
Exactly, exactly. So in the Stokes' second problem, we had a characteristic time scale. We also had a characteristic velocity. We may choose this characteristic velocity at the plate velocity and or like whatever we wish. So since we had the command over at least two scales, we could use the method of separation of variables. But in Stokes' first problem, we only know what will be the characteristic velocity, but we don't know what is the characteristic time scale and the characteristic length scale. Okay, so here the only scale that is not known trivially is the characteristic length scale, but we know what will be the characteristic time scale and the characteristic velocity of the problem, velocity scale, which was not the case in Stokes' first problem. So in first problem, we only knew the characteristic velocity. However, we didn't knew the characteristic time and the characteristic length scale. So the basis of the unknown of so the basis by which these scales are not known essentially led us into following two different paths. So when these scales are not known and we don't know how the velocity will actually turn up and we don't have a command over the two variables, we use something which is called a similarity variable. So the idea of using a similarity variable is that we club the variation of the two variables into a single variable, which you may call eta or lambda or whatever you wish. So the idea is that if the solutions are self-similar, then we can club them into the similarity variable as you saw in last week. However, in the Stokes second problem, since we know how the time scale would basically vary and also we had a defined velocity scale, we use something which is called the method of separation of variables. So that's why the scaling analysis is very much important and the idea of developing these scales is very important. Okay. So this is something that I want to put forward here before starting the problem. So now we will solve a similar problem, which is basically the time periodic pressure driven flow in a cylindrical channel. And I will describe the problem first. But before that, if you have any doubts regarding this week's session, the lecture sessions and the previous weeks in lecture sessions and the interactive session, I'll wait here for 2-3 minutes. You can put forward your doubt, or like we will begin in maybe 3, 4, or 5 minutes with this problem.
Hello. So can I ask one doubt regarding one assignment question in this week's? Actually, in
Yeah,
question
sure.
ninth, it
Yeah,
is
sure. Huh,
in week five's assignment ninth. It is
huh.
not clear whether we have to find average velocity or
Okay. So can you tell me the
humans.
number actually? This
Ninth,
question 9, which week?
week five.
Week 5. Okay. All right. So let me check once
Okay.
because I don't have the assignment now with me, but I need to check it in my system. I'll just check. Uh, just check that. So this is, hold on. I'll just check that. Okay. So what was your doubt? Can you repeat?
Do we need to find an average velocity in
The
that?
axial flow velocity through the constant.
Yeah. Or is it U max?
Okay. So to me, I think this is so since they're asking consider the flow situation, the axial velocity in meter per second to the constant cross sectional duct. So since they're asking the axial velocity, I think you need to find, so the axial flow velocity is basically the velocity at the axis, right? So I think you need to find the umax. Okay. However, I'll check this out. Okay. I just need to like so to me it appears to be the maximum velocity. But I'll check this out and I'll post it. So basically I'll check this out and I'll post it in the discussion forum of this group and I'll try to clarify it if I have the information with me. Is it okay?
Yeah. Okay. Okay. Thank you.
Sure. Okay. So I will post this out. Meanwhile, I'll just write it. So it is U max or U average. All right. Okay. This is file. One second. Okay. I'll post that in the discussions group. Okay. All right. So let us begin. Let us begin in this week's session. So, what we were supposed to do today is like we will basically try to solve for the flow profile when there is a fluid that is that is just traveling through a pipe where the actuating pressure gradient is given by this minus dp by dz, which is basically an axial pressure gradient. However, in the earlier cases, as we saw that in Hagen possible flow, the pressure gradient is basically constant. However, in this case, the pressure gradient is not constant, but it is some constant multiplied by an oscillating factor of time, which is basically cos omega t. So this means that since this is an oscillating pressure gradient, so essentially if I plot this pressure gradient, let's say dp by dz with let's say time, our curve would basically be something like this. So this means in some instances or in some instances of time, we will have a favorable pressure gradient, or I mean favorable means we can have a pressure gradient in the plus z direction, and in some cases we can have this dpdz as in the other direction, which means that since due to the oscillating nature of this pressure gradient, now the fluid will also move back and forth. So maybe at some time the velocity profile would be something like this, and in the other instant of time, the velocity profile would be something like this, or maybe something like this. Okay, so this is something that we are essentially going to find out. However, the crux of this problem is that we will solve this problem non-dimensionally by finding the characteristic scales of the problem. We will use non-dimensional variables into solving this. Okay, so I hope the aim of the problem is clear. What we basically need to do uh, in this case, where I would just say that this mu and rho are basically the dynamic viscosities and the density of the fluid. Okay, so the objective is to of course derive a non-dimensional governing equations and the boundary condition and solve for the velocity profile. So I hope this problem is clear. I'll just pause here for 1 or 2 minutes so that you can understand this, and then we will begin with the solution in a systematic way. All right. So before me solving this problem, I'll just state the assumptions here. Okay. So the assumptions are the following. So we will consider the flow to be unidirectional. So I'll just write unidirectional flow, which means, so what does this mean? This means that ur and u theta will basically be equals to 0. Of course, since this is a pipe, since this is a pipe, we'll use the cylindrical coordinate system. And this means that ur and u theta is 0 because we are invoking the unidirectional flow assumption. And of course, this has to be 0. That's simply because ur is 0 because of the no penetration boundary condition. U theta is 0 because there is no flow or there is no actuating force in the theta direction. Okay. The second assumption is that we will follow or we will use the fully developed assumption. So the flow is fully developed, which means, so what does it mean? This means that uj is not a function of z. That is what it suggests. We will follow one more thing, that is constant properties assumption. So we'll follow the properties varying constant values. And the fourth thing is not an assumption, but what we seek is that, so we seek time periodic solution. Okay. So this is, so these are basically, so I won't say this is an assumption, so let's not write it as an assumption, but so our solution will now have time as a parameter in our analysis. Okay. So basically these, so the 1, 2, 3 are the assumptions, and we now seek time periodic solution as you have rightly said for the, so we'll begin with a similar process, just how we did in solving the Stokes second problem. Okay. So if this is the case, you can, so rest assured, you can show that the continuity equation is trivially satisfied because u r and u theta is 0, and we will eventually see that del uz by del z will be 0, which means that uz is not a function of z. So the continuity equation, using the fact that the fully developed assumption is considered, is trivially satisfied. Okay, so that's why we will not write the continuity equation here, because we have done this many a times. What we will do is, we'll begin with the z component of the Navier-Stokes equation, because now we have just the uz velocity. So we'll begin with the z component of the Navier-Stokes equation. Okay, and since we know how to invoke the assumptions, I would straight away start off with its simplified form. Okay, that is by invoking all the assumptions that we have said. Okay, so I'll just start off with the simplified form. So the simplified form basically looks something like this. So it is just rho times del uz by del t, that is equals to minus del pz plus mu by r del r of r times del uz by del z. Sorry, del r. All right. So can you tell me, had the pressure gradient uh, is not, so had the pressure gradient is not oscillatory, or otherwise it's a constant value, which term in this equation would just drop to be 0? Can you tell me?
dp by dz.
dp by dz would go to 0.
No, sorry.
Okay. So can you tell me which term would go to 0 then? So my question is, instead of having, so I'll simplify the question. So instead of having dp by dz, or instead of having this dp by dz as g naught cos omega t, but I'm saying that I just have
du
dp by
by
d.
dt.
Yeah. Which one?
du by dt. duz
Yes,
by dt.
duz by dt. Yeah, exactly. So that's obvious, right? Because if the pressure gradient is constant, okay, then we'll not have this
It's like
unsteadiness.
Hagen-Poiseuille
Yeah,
law.
it's the Hagen-Poiseuille flow only. So if you solve this, so it just, so if you just solve this, you'll basically get that Hagen-Poiseuille flow and that parabolic velocity profile that you know. However, the essence of adding that oscillatory term is basically what leads to solving into a PDE, which we earlier solved as an ODE in Hagen-Poiseuille problem. So I hope the difference is clear this time. Okay, so since we know that this del p by del z, or since this should be dp by dz, basically because the pressure gradient is only in the axial direction, but we know that since this value is g naught times of cos omega t, we'll just substitute it here. Okay, and let's see what we can. So it is del uz by del t, that is equal to, what is this? So is equals to g naught of cos omega t plus mu by r del r of del uz by del r. Okay, so we will, although you have said, I will acknowledge like two things here. So first of all, this is a PDE. First of all, this is a PDE instead of an ODE. Okay. And since this is a PDE, this UZ, as you can see, is a function of R and is also a function of time. Okay. And this leads to us following a different approach into solving PDEs. So there are specified techniques of solving PDEs, as we have seen. So the similarity variable is also one technique. Method of separation of variables, as you will see, that is also one more technique. Okay, so there are many ways of solving PDEs. Okay, but the essence is that since this is not an ODE, so it eventually leads to solving a variable UZ, which is basically a function of both R and time. Okay, but as we will see, whatever bit of PDE technique that you are using basically to solve a partial differential equation, every time it always boils down into solving an ODE only, as we will also see here. So we will invoke certain forms of this solution into this governing equation, and our main objective is to transform this PDE into an ODE. Why? The very straightforward reason is that we know how to solve ODE. So analytically solving a PDE by hand is very difficult. So every time you get a PDE and we seek to get an analytical solution, our objective, or at least our first objective, is to convert that PDE into an ODE. Okay. So that's the idea. So that is what I wish to uh, speak forward here. So yeah, so I'll just name this equation, and since this is the first kind of problem that we are solving, I'll just proceed very slowly. Please let me know if you have any doubts and stop me wherever you wish to clarify certain things. Okay. So before so the idea is that we'll use the characteristic scales, but before using the characteristic scales, can you tell me what will be the boundary conditions here?
Yeah. No
Yeah,
slip boundary condition.
exactly. So first one is that UZ at
At,
R equals to capital R for all time, that is 0, which, as you have rightly said, is the no slip. The second one, can you tell
is
me
the
what will be the,
dou
yeah,
uz by dou r is 0 at r
exactly,
equal to 0.
exactly. So dou UZ by dou R at R equals to 0, which basically means that UZ is finite, and this is 0 due to symmetricity. Okay, due to the symmetric nature of the problem and due to symmetry. All right. So dimensionally, this is the equation that we will solve for, where this rho is basically the density, mu is the dynamic viscosity. This is the given oscillating pressure gradient with amplitude G naught, and these are the two boundary conditions. Okay. Now, what we will do is we will use the knowledge of our scaling analysis that we learned in the last class into transforming this dimensional equation into a non-dimensional equation. All right. So, but in order to non-dimensionalize the given equation, we first need to understand what are the characteristic scales of our problem. Okay. So first of all, as you have rightly said, the characteristic time scale TC. So can you tell me what is do we have a characteristic time scale in this problem? Do we have a characteristic time
Yes,
scale? Yes. What is that?
1 by omega.
Exactly. Omega inverse. So characteristic time scale is basically omega inverse. Okay, which is also known as the imposed time scale, because that is directly given to us by the physical problem. Okay, this is known as the imposed time scale. Similarly, do we have a characteristic length scale of this problem?
Yes,
What is that?
diameter of m.
Yes, exactly. You can either choose diameter or the radius. The answer won't be
Yeah.
hampered by this. For the sake of simplicity, we'll choose the radius at the characteristic length scale. Okay, all right. Now, here is the thing. So what do we need? We have a characteristic time scale, we have a characteristic length scale. Again, as I said, since we now have both the characteristic time scale and the length scale, this basically hints us, so there should be a bell that is ringing, that should ring into your mind, that now we can use method of separation of variable without using the similarity analysis or other techniques. Okay. So if we have that, can you tell me based on this information, first of all, do we have a characteristic velocity scale of this problem? Do we have a defined velocity scale?
We can define LC by TC.
Exactly. So we can define LC by TC. That is true, but that is true.
Or we
But then,
can center line or
yes,
average.
yes, true. That is true. But here is one thing that I would put forward here. Yes, we can. You can define. So what you said is right, that we can define this by as LC by TC, where LC is basically what it is R and TC is basically one. So R omega is basically your characteristic velocity. That's what you said. But see, here is again the catch in like choosing characteristic scales. Okay, so basically the the driving force which is actually acting on the fluid, which drives the fluid, is basically the pressure gradient. Okay, and it is actually the amplitude rather than the oscillating term which basically drives the fluid. Okay, that's why even if that LC by TC can be chosen as a characteristic scale, the more right scale into choosing the characteristic velocity is something like this. Okay, I'll just say to you that this is also an alternative way of choosing this characteristic scale, and I would just point it out here. So what I would do is, I will just compare this term with this term. Okay, that is again because the pressure gradient is essentially driving the flow. Okay, so what I would do is, so for the for characteristic velocity scale, what I would do is the order of this, so the order of this minus dp by dz, I would say, is of the same order of this term, mu by r del r of r times del uz by del r. Okay, which is basically these two terms. Again, the idea is that it is the pressure gradient that is actually driving the fluid and not the other way around. Okay, so now if we do an order of magnitude analysis, can you tell me what is the order of this term which is minus dp by dz?
G naught.
G naught, exactly. So the order of this term is G naught, and it is not G naught cos omega t. That is simply because cos omega t is just an oscillating function between 1 and minus 1. So the order of magnitude will always be dependent on that G naught. If G naught is large, the order of magnitude will be large. If G naught is small, the order of magnitude will be small. However, this does not make sense when t becomes equals to 0, but the the dictation on the order of this dp by dz will depend on 0, and that's why we will say that this term, the order of the term minus dp by d naught, is g naught. Okay, and in a similar way, the order of magnitude of this term would be what? Can you tell me what will be the order of magnitude? Like, so we did this in the last class. Can you tell me how to find out the order of magnitude of this term?
Mu c u c by r square.
Yes, so it is mu c u c, so it is mu c u c by r square. Okay, which means if the uc, which is the characteristic velocity, would scale as g naught r square by mu. Okay, so this is basically the velocity scale for our problem. All right. Okay, so we have defined all the necessary scales. So we have the necessary time scale, which is this. We have the necessary length scale, which is this. We have the necessary velocity scale, which is basically g naught times r square by mu. Okay. All right. Now, before proceeding, I will again stop here for 1 or 2 minutes. If you have doubts, you can ask. But I hope this is trivial because we did this many a times in the previous week's session. Okay. So the next step. So okay, before going to the next step, I'll just stop here for a couple of minutes. In the meanwhile, I am just thinking that this is one way of choosing the characteristic velocity. You can also choose the characteristic velocity as LC by TC. Okay. And if you choose that, I'm just thinking how so essentially the problem should not change, because however way you non-dimensional the problem, the dimensional problem remains the same, right? So later on the problem should not change to me, but okay, this is a good test also for you to try it out. Like if you choose the velocity scale, you see as that, I mean, as just LC by TC and try out the problem, non-dimensionalize it, and maybe you can give me the answer in the next class. Like how does it change? Does it ever change? Or if it changes, like how does it change? Okay. The dimension, of course, keep in mind that a dimensional velocity, so the resultant dimensional velocity field that you get at last should always be the same, and it is irrespective of whichever scales that you choose, because we are choosing the scales, right? The nature doesn't choose the scale. So the final answer, if you write it in the dimensional form, should always remain the same. That's the essence. Okay. Although the non-dimensional form may be different, but a dimensional form will always be the same. All right. Okay. So the next step is important. Okay. So once we are done choosing the scale, the next step is to define the non-dimensional variable. Okay. So I would write here. So I'll also systematize it by writing the steps. Okay. To the first step. So this is step one. This is step one. The step one is choosing the characteristic scales. I'll just write choosing the scales. Choosing the characteristic scales is the first step. Step two is basically defining the non-dimensional variables based on the characteristic scales. All right. Okay. So we define the non-dimensional z direction velocity as uz bar. And can you tell me what will be the form of uz bar?
U by UC.
Exactly. So it will be uz by uc. In the same sense, the non-dimensional radius r bar would be just r by the capital R, which is LC. This is basically LC only. And the non-dimensional, what we have, the non-dimensional time t bar would be, so what it, so the t bar would be t by tc. Tc is omega inverse, so t bar would essentially be omega times t. Okay. All right. So far, so good. So just this is the first problem that we are solving. So I'll just write here. So this is basically the non-dimensional velocity. Velocity. And similarly, this is the non-dimensional radius and the non-dimensional time. Now, can you tell me what will be the order of magnitude of these non-dimensional terms? Can you tell me? Yeah.
One around.
Yes, exactly. This is something that you need to understand. So, the very essence of deriving the non-dimensional variable is that the order of magnitude of all the individual variables will always be order 1. Okay, see, uj could be anything. It could be 10 to the power minus 3 meters per second or mm per second. Okay. However, since we, as I have already said in the last class, the essence of defining the characteristic velocity is that now the characteristic velocity should be of the ballpark figure of the actual velocity. Okay. So when we are dividing it by the characteristic velocity, this means that these non-dimensional variables will always be order 1. Okay. This is the essence of defining non-dimensional variable, and this gives us a freedom and it gives us a clarity of understanding. So this simplifies our problem. Okay, this simplifies our problem, and this brings up a clarity into getting the results, because now we don't need to deal about the large numbers or the small numbers or different properties, but we will only be interested in numbers, and that's why we this essentially simplifies the problem. Okay, so the next step, so we have defined the characteristic scale. The third step, step 3, is insert. So sorry, we have defined the characteristic variables, and then we have defined the non-dimensional velocities, the non-dimensional radius, and the non-dimensional time based on the characteristic scale. And the third step is to insert this into the governing equation. So insert the non-dimensional variable into the governing equation, which is basically what? So our governing equation was 1, I think. Yeah. All right. Into 1. So if we do that, let's see what we get. So I'll rewrite. So let's do one thing. Let's see the governing equations again. So this was basically our governing equation. And paste it here. All right. So now let's write the dimensional variables, that these dimensional variables in terms of the non-dimensional variables. So if we do that, let's see what do we get. So the term on the left hand side would be rho times u. So remember, u bar was basically u times. So u bar was basically u times uc. So this u becomes u bar times uc. Okay. So that's why I put the uc out. So this becomes rho times uc by tc times del uj bar by del t bar. I hope this is clear. If it is not clear, please stop me and let me know. These terms become so what does it become? This becomes g naught times cos omega t becomes t bar, because we already saw that t bar is basically omega times t. Okay, plus from here what do we get? So we get mu uc by rc squared, okay, times 1 by r bar. Okay, so did we do this correctly? Or yeah, I think we did this correctly. So 1r and 1r would go. Okay, so it is 1 by r bar del r bar of r bar times del uj bar by del r bar. Okay, please check the algebra and just let me know if I make any mistake. All right, now since you already know that uc scales as g naught rc square by mu, we will substitute the value of uc's there. Okay, so and let's see what do we get. So it is rho tc is just omega inverse, so this becomes omega. Okay, and uc is what? Uc is g naught times r square by mu. Okay, is g naught r square by mu times del uj bar by del t bar, and this becomes g naught times cos of t bar. Okay, plus, so it is mu. So it is, so we have mu. What do we have? We have mu uc by rc square. So we'll write mu by capital R square and uc. So what? So uc is g naught r square by mu. So this becomes what? This becomes g naught times r squared by mu. It is just the algebra that I'm doing. So there's nothing to explain much here. This becomes r bar times del r bar of r bar times del uj bar by del r bar. All right. So let's do some, what do we do? Let's do some simplification, okay? So this G naught and G naught cancels out, right? And, all right. And what we have? And this R squares also cancels out, okay? Okay. And what does cancel? Okay, so I think there is this one mu here. Okay, and this should be mu. I feel this should not be mu squared, this should be mu. So this mu and this mu cancels out. That is simply because uh this uc is g naught rc squared by mu. Okay, that's why this should be mu and this cancels out. Okay, which means we just end up. So I hope the algebra is clear. Please let me know if there is any doubt. Okay, so which means we end up getting rho omega r square by mu times del uz bar by del t bar is equal to cos t bar plus 1 by r bar times del r bar of r bar times del uz bar by r bar. Okay, all right. So I hope this is clear. So now what we'll do is we will simplify this term as follows. Okay, so what we will do is we will write this term as rho times omega r, okay, times r divided by mu into del uz bar by del t bar, and this is cos of t bar plus 1 by r bar del r bar of r bar times del uz bar by del r bar. All right. So let's now have a look at this term. Okay. So this term is what? This term is basically rho times, it is rho times omega r into r, okay, by mu. Now, can you tell me, do you see some similarity of this term with some number, or in other
Reynolds
words,
number.
yeah, exactly. This looks like a Reynolds number. However, this is not exactly the Reynolds number, because there is this omega, which is basically the frequency factor that comes into the play, and that's why this number is known as the frequency dependent Reynolds number. Okay, so this number has got a name. This is known as the frequency dependent Reynolds number. And we will denote this number as alpha squared. Okay, so the final non-dimensional equation, okay, I said it is non-dimensional, but I'll throw light on it. So but let me first write it down. So the final non-dimensional equation basically looks like alpha squared del uz bar by del t bar, and this becomes cos of t bar plus 1 by r bar times del r bar times r bar del uz bar by del r bar. All right, and we will name this. What do we name? We'll name this as equation 2. Now, can you tell me what is the dimension of this equation?
No dimension.
No
Non-dimensional
dimension.
also.
Exactly. No dimension. Which means that, see, yes, of course it is non-dimensional. But if you have a deeper look, what does it mean? This means that if we anyhow solve this problem, if we anyhow solve this equation using some boundary condition, and we find out the non-dimensional uz, the non-dimensional uz will just be a function of this alpha square. This means that, so in other words, if I tune alpha, if I tune the value of alpha, I will get the value of uz as a function of r bar and t bar. Okay, so in other words, I don't need to bother about the quantities like rho, mu, okay, or so on and so forth, omega, or so on and so forth, which means that all the dimensional quantities is already embedded in this frequency dependent real number. So I may choose alpha equal to 1, I may choose alpha equal to 10, I may also choose alpha equal to 15, and this will throw out the value of uz bar. That is the essence of actually solving non-dimensional equations. Okay, we don't need to simultaneously tune the different properties, but we tune the non-dimensional number that associates with the individual properties. Okay, so this is the non-dimensional equation. So we will shortly take a break, but break means a 5 to 3 minutes break, so that you can understand. But before that, this is the non-dimensional equation, and we also need to write the boundary conditions in the non-dimensional form. Okay, so can you tell me what will be the boundary conditions non-dimensionally? So equation 3 is subject to what? So this is very simple. So yeah, go ahead.
UZ at R equal to At r bar equal to 1 is
Exactly. Yeah.
0.
So that is the essence. That is the essence. So earlier it was UZ at R equal to capital R for all time was basically 0. But now since we are defining it non-dimensionally, so UZ at R bar at equals to 1, because our characteristic scale is itself the radius, so that R bar equals to 1 for all time t is equals to 0. And this is basically what? This is basically the no slip, as you said. And secondly, Secondly, the boundedness criteria, that the derivative with respect to r is basically 0, or in other words, the boundedness criteria can also be written as uz bar, okay, uz bar at any r bar is always less than infinity, which means this is the same way as saying that uz by ur at r equal to 1 is equal to 0, but here we will use the just the finiteness or the boundedness criteria, just to make things similar with the Stokes second problem, because I think in the Stokes second problem you basically did something like this only in the far field scenario. That is basically just the same. So this is again, so this condition, so I again repeat, this condition is exactly similar to the fact that duz, or I mean del uz by del r, del uz by del r bar at r bar equals to 0 equal to 0. So both the things are same, and they are simply the finiteness criteria, okay, finiteness or the boundedness criteria, finiteness or boundedness. All right, and I'll just name it as what, this is 2a, and of course it's 2b. Okay, so we'll stop here for some time. And next, what we need to do is we basically need to solve this equation 2 subject to these two boundary conditions. Okay, but before proceeding that, I'll stop here for some time. I'll just come in 1 or 2 minutes. In the meantime, you can recapitulate what we did so far, and if you have any doubts, you can let me know. Okay. All right. Uh, Before beginning the solution, I would just like to ask a interesting question here. So the thing is, let's first of all have a look at the physical picture. Okay, so what was that? It was something like this. So the physical picture was like there's a tube and there's an oscillating pressure gradient, which is basically something like this. So this is what the problem says. Okay, but can you tell me in what practical applications do we encounter such oscillating pressure gradients and the resulting flow that occurs due to this oscillating pressure gradient? Can you think of it and tell me? Like, so if this pressure gradient is constant, that is just flow through pipe. Okay, that is the simple household. So it's everywhere. Okay, flow of water through a household pipe, or flow of some gasoline or something like this through pipes, the piping system, and so on and so forth. But where do we encounter this oscillating pressure gradient in practical sense? Such oscillating scenarios. Okay, can you tell me? You can think about it. Maybe in 1 or 2 minutes you can think. If not, I will tell the answer in the next class. I'll give you a week's time to think, although it should not take a week time. Okay. So let's get started with the solution. Okay. So the idea is that we need to solve. So before that, what did you do? So we started off with the dimensional governing UZ moment. I mean the Z momentum equation. We defined the characteristic scales. We defined the non-dimensional number pertaining to those characteristic scales. And then what did you do? We substituted that non-dimensional numbers into the dimensional governing equation. And then we simplified the equation, which basically looked something like this, and subjected to these two boundary conditions. However, as I said, this is still a PDE, right? And we need to look for strategies to solve these PDEs. So what we will basically do is, so the way of solving this problem, just 1 second. Yeah, 1 second. Okay. Okay. Sorry for the interruption. So what do we do now? So the next steps are, so what was our step? So this will be step 4, I guess. It's step 4. Step 4, and that is the solution procedure. All right. So can you tell me how do we solve this problem? Can you just give it a try?
Like Stokes' second problem, assuming
Yes,
some
exactly. So what do we do is that is very like so that's a very standard way of solving such kind of problems. Okay. So what we do is we assume uj bar, r bar, and t bar, which is basically a variable which is dependent on both r bar and t bar together, as something like this. So we assume this solution to be of the form some real part of u hat of r into e power I t bar. Okay. Again, the essence of choosing this form is that we know that our solution will be time periodic in nature, and that's why we know that how the function. So see, this is a way of, so what is this is basically separation of variable only, right? So we are separating a dependent variable which is dependent both on r bar and t bar into two variables, one a sole function of r bar and a sole function of time. However, we know a priori that the function of time would be oscillatory in nature, and that's why we have chosen it as e power I t bar. Okay, had we don't, so had that problem been not oscillatory in nature and it is just some two random functions, for instance, the flow. So if you see the weeks 5 content, it is just flow through a rectangular channel. Okay, there you cannot assume the other function to be of this form. Why? Because that in that case, so there is no oscillatory business that is happening there. Okay, so that's the idea. In essence, this is just separation of variable only, but a priori we know that the solution would be oscillatory in nature, and that's why we have in advance we have just chosen the time function to be something like this. So that's the essence. Okay. All right. So we assume this. So okay. So what next? So it's fine that we assumed it. So what next do we need? So what should we do now?
plug this in the OD,
Yeah,
PD.
exactly. So what we do is we just substitute this tree into equation 2, basically. All right, let's do it. Mm. So what? So we have this term. Okay, what do we have? We have alpha squared del uj bar by del t bar, which means, so if we just plug this thing into this here, what do we get? So we get I alpha squared. So it becomes I alpha squared. Okay. And yeah, so this is I alpha squared. This del t term would basically go out. So it becomes real part of u hat of r e power I t bar. Okay. I think this is fine. So what we did is we just substituted this UZ, we just substituted this UZ here. So since there is just a time derivative, this means this I would basically come outside, and that becomes I alpha squared, and this term would even inevitably be the same. Okay. So let's see the other term. So the other term is basically cos t bar. So we can do one thing. We can write cos t bar So what is cos t bar? Cos t bar is nothing but, so it is just real, so it is a real of e power I t bar, right? Why? Because e power I t bar, if you expand there, it is just, so what is e power I theta? It is cos theta plus I sin theta, right? So the real part of e power I theta is just cos theta. And that's why what we did is we just we went the reverse way. We said that cos theta is basically the real part of e power I theta, and theta is t bar here. Okay. All right. And the other term, so what is that? So it is just 1 by r bar times del r bar of what? R bar times, it is del u, so it is del uz bar by del r bar. Okay, so this becomes 1 by r bar, it is del, so uz is just this, so it, so what does it become? It becomes del r of u hat of r e power I t bar, and of course there has to be a real part here, but let's write the real part here. And if we simplify this, so we are just substituting and simplifying, so there's nothing new here. So if we simplify this becomes what? This becomes real part of, okay, e power I t bar into 1 by r ddr, in fact this would be r bar, ddr bar of du hat of r by dr, u hat of r bar by dr bar. The reason why this changed from del to d or do to d is because we have separated the variable, and hence the del or the do operator will just be a d operator because u hat is just a function of r. All right. So these are the individual terms that we evaluated. So the first one was this term, the second one was this term, and the third term is basically this term. So we'll just substitute it and let's see what do we get if we substitute that. So the left hand side becomes I alpha squared, okay, I alpha squared, and what does this become? This becomes, so see, u hat of r is the real number only, right? So I can take this u hat of r outside this real part. So this becomes I alpha squared u hat of r, and this becomes real part of e power I t bar. Okay. And cos t, as I have already said, it is nothing but real of e power I t bar. Okay. Plus, what do we have? Plus real of e power I t bar into 1 by r bar dd r bar of r bar times du hat of r bar by dr bar. All right. So what did it do? We just substituted it. Okay. We just substituting the individual terms. All right. Now what we can do is this real of e power I t bar, we are assuming that this is not 0, because if that is 0, then u hat of r will always be 0, and that's a trivial solution, right? And we are not interested in trivial solution. So this real of e power I bar, we are assuming it is non-zero, and then we can then we can basically cancel this term, and then we end up getting what? It is I alpha squared u hat of r is equal to 1 plus 1 by r bar dd r bar of r bar times d of u hat of r bar by d r bar. Okay. And we will just basically simplify this using the chain rule. And if you do that, let's see what do we get. So we get what? And I bring this term into the other side as well. Okay, let's see. So I hope I'm doing this correctly. And there is no mistake here. Yeah, I think we're doing it correctly only. Yeah. All right. So let's simplify this. So this term becomes d2 u hat of r bar by dr bar square. What you do is you just apply chain rule here. Okay. and the second term will become 1 by r bar, okay, times du hat of r bar by dr bar. Okay, these are the two terms. And what do we have? We have what? We have, so what I do is I bring this term here and I take the constant term the other way. Okay, so this becomes minus I alpha squared u hat of r, and this becomes minus 1. Okay, so if I just write it down once again, just in the next page, so what do we have? We have d2 u hat of r bar by d r bar plus 1 by r bar du hat of r bar by dr bar minus I alpha squared u hat of r bar, this would be r bar, and this is equals to 1. All right, so we have successfully transformed the PDE into an ODE in u hat of r bar, and all we need to do now is to solve this ODE. Okay, so let's name this as what? Let's name it as equation 4 maybe. Let's name this as equation 4. Okay. All right. So, as I have said, 4 is an ODE. Okay. But can you tell me what is the type of this ODE? What is the, first of all, what is the order of this ODE? Then, what is the nature? It is homogeneous or non-homogeneous? It is is it constant coefficient or variable coefficient? These three things you need to tell me. Okay. First, the order. So what is the order of this ODE?
Second.
Exactly. It's a second order ODE. Is it homogeneous or non-homogeneous?
Non-homogeneous.
Exactly. The reason behind is that u hat of r bar equal to 0 is not a trivial solution of this ODE. Or in other words, if I put u hat of r bar equal to 0, I don't get the left hand side to be equal to right hand side, and that's why it's a non-homogeneous ODE. So it's non-homogeneous, of course. And is it a constant coefficient ODE or a variable coefficient ODE? That's trivial, right? Is it a constant coefficient ODE or a variable coefficient ODE?
Wait,
Variable, yeah, exactly.
variable.
Because we have an r bar here, right? We have an r bar, 1 by r bar here. So this d, so it's called variable coefficient because the independent variable is also multiplied with the dependent variable. Okay, that's why it's a variable coefficient ODE. So what is, so if this is the case, so then how do we solve this? So what is the way of solving such, so how do we solve such ODEs? Second order non-homogeneous variable coefficients. Do you remember how do we solve this? Yeah.
Standard Bessel function. Bessel D.
But Bessel, see the Bessel's equation or the Bessel, so the Bessel equation and the solution of those Bessel equation are basically the Bessel functions. First of all, the Bessel equation is a homogeneous. It's a homogeneous ODE, right? You can look into the net. It's a homogeneous ODE. That's the first thing. Second thing, this does not exactly fit into the Bessel equation. Okay, this does not exactly fit into the Bessel equation. So we need to modify it. So idea is that we need to modify it into the Bessel equation. And but that's not a standard way. There is a standard way of solving these kind of ordinary differential equation. Yeah, go ahead.
Homogeneous equation plus particular.
Exactly, exactly. That's what I was actually looking for. So the answer is u hat of r bar basically would be now the complementary function, or you can tell the homogeneous part. So it's so we'll say that it is uc of r bar, which is basically the complementary function, and the complementary function would satisfy the sort of those Bessel equation. Okay, we will see that shortly, plus the particular integral that we will write is at up of r bar. Now, thankfully, luckily or unluckily, we can very easily find out the particular integral here. There are numerous ways of finding particular integral. There are many ways, but in this case, the particular integral is very simple. Okay. Can you tell me what will be the particular integral just by looking at this equation? I'll give you a hint that a particular integral, okay, should satisfy the particular integral to satisfy the governing equation that you know, right?
Constant or not?
Exactly. The particular will be integral will be a constant, but what is that constant? What is that constant that you can figure out from this equation itself? Okay, using the fact that the particular integral should satisfy the equation. So the most common and the obvious constant of this is as follows. Tell me that I'm correct or not. So the particular integral up of r bar, I would say, is just going to be 1 by I alpha squared. Okay. Why? That is simply because you take this form. That is simply because, see, the idea is that had there been a variable on this non-homogeneous part, or in for instance, had there been a function of r bar, if there has been a function of r bar, then by inspection we cannot say the particular integral is that. But since this is a constant, luckily we don't need to explicitly solve the particular integral, and just by inspection we can say that the particular integral would be just constant divided by the coefficient of just u hat. Okay, so that's why it became 1 by I alpha squared. And you can prove yourself. Just substitute up as 1 by I alpha squared into this equation. So what happens when we substitute this term as 1 by I alpha squared? So the first derivative would go because it is just a constant, and similarly the second derivative. And this is just 1 by I alpha squared. So this would get cancelled. So you will just get -1 equal to -1, which means it holds good. Okay, so the particular integral in this case becomes 1 by I alpha squared. Okay. All right. Now, the other part, the complementary function. So, what equation does the complementary function satisfy? So, this is the particular integral. This is the particular integral. Yeah. Can you tell me what equation does the complementary function satisfy based on this?
Bessel equation.
Yes, true, Bessel equation. But yeah, we will get in the Bessel equation. But the complementary function satisfy the homogeneous part of this equation, right? That's what
Yeah, yeah.
mathematically mean, right? Yeah. Okay. So you see, you had C would satisfy this. So you had C satisfies this. Okay. So it satisfied what? It satisfies the complementary part, which is basically what T2 UC hat by TR bar squared plus 1 by R bar T U hat by TR bar minus, I think there is a minus here, minus this would be C I alpha squared d q hat C equals to 0. Okay. I just check my notes here just to be sure that we are on the same page. All right, so I think this is fine. Yeah. Okay. So what we will now do is, as you said, we need, so this basically give us a hint that we are some way approaching to the form of the Bessel equation, but this is not exactly the Bessel equation. In fact, we need to do a change of variable here. So I'll show you how do we need to do. But before that, let's do one thing. Let's multiply this entire equation by r bar squared. Okay, and let's see what do we get. If we multiply that, we get what? We get r bar squared d2u hat c by dr bar squared, okay, plus r bar times duc hat by dr bar minus I alpha squared r bar squared by uc hat equals to 0. All right. So now what we'll do is we will do a change of variable. We will do a change of variable, and we will define a variable r tilde as r bar alpha root I. Why? We will see shortly. So this means this term would basically be r tilde squared. Okay. And similarly, if you apply this change of variable in these two terms, they will simplify as follows. Okay. I'll just write it down here. So we'll do this change of variable. So this is this change of variable. So these are just mathematical tricks, okay? You just, so it doesn't just come, so it is not an ad hoc thing that is that is what we are doing, but these are just mathematical tricks and substitution that you need to do basically to get analytical solutions. Okay, so if we use this change of variable into these things, because now we need to change the equation from r bar to r tilde. So what we will get, it we will get duc hat by dr bar as alpha times root over I. You get duc hat by dr tilde. Okay, and similarly this d2uc hat by dr bar square, you will end up getting alpha square I times d2uc hat by dr tilde squared. All right, so again, what next? So what we will do is we will use this change of variable into this governing equation. Okay, then let's see what do we get. So what we get is just, so it's just simple, just substitute all these things, just substitute all these things into this, and then as you do, so I'll not do the math here, it's just straightforward. So what you will get is as follows: you will get r tilde squared, okay, d2uc hat by dr tilde square plus r tilde times duc hat by dr tilde minus r tilde squared uc hat equals to 0. Now we will see what you are already like telling, what you already told few minutes back. Okay, so this is the simplified equations after doing all those change of variable uh, that we basically did. Okay, so let's name this at equation 5. Basically, let's name it at equation 5. Now this is important. I know you, I mean you have gone through it, but again I'll just tell it for the sake of like clarity. Okay, so if I have a dependent variable u, which is basically a function of x, okay, then the Bessel equation which governs u of x is as follows. Okay, it is x squared times d2ux by dx squared, okay, plus x du dx plus x square minus nu square times u of x equals to 0, where this new is known as, so what is new? Can you tell me what is new?
0.
Yeah, for this case it is 0, but in general what is new? So it's the order of the Bessel equation, right?
Yeah, order.
Yeah,
Yes.
so this is known as the order of the Bessel's equation. Okay, so if I now if I now so yeah, but there is one catch. So if I now compare this and this, I get two insights. First of all, this new is 0, as you can see, but there is a minus sign here. So what I now need to do is, there is also something which is known as the modified Bessel equation, and the modified Bessel equation is basically this. Okay, so there is a minus sign here. Okay, then if there is a minus sign, this is known as the modified Bessel equation. You can just go through the, you can just see in the internet what is a modified Bessel equation. Okay, so this is not exactly a Bessel equation, this is basically the modified Bessel equation. Okay, so that's why uh, this is known as the order, so this is known as the modified Bessel equation. Just so it is just like the Bessel equation, but so the solution, so as you know, the solution of the Bessel equation are the Bessel function, the solution of the modified Bessel equation are the modified Bessel function. Okay. All right. So based on that, can you tell me what is the order of this modified Bessel equation? Can you tell me? As you said.
0.
Exactly. So now, since I know that this is my modified Bessel equation, so the solution of this equation u of x is nothing but the Bessel functions. Okay, so it is just a times, it is some j nu of x plus b times j, so it's just b times y nu of x, where these j and y are the solutions of the modified Bessel equation, and they are known as the modified Bessel function. Okay, so this j nu and y nu. So the idea is this j nu and y nu, these are the modified Bessel function. All right. So in the same spirit, u hat of c as a function of r tilde would just be some, let's say, a1 j0 of r tilde plus b1 y0 of r tilde. Y0, that's simply because the order of our Bessel equation is basically 0. All right. So we are almost there. We are almost there. Okay. So now, how do we evaluate these two things, A1 and B1?
Boundary conditions.
Yes, exactly. So we use the boundary condition. So let's name this. So let's name this solution as what? Let's name the solution as 5A, basically. So we now use the boundary conditions. But first of all, let's convert the tilde. So let's convert the tilde thing. Okay, but okay, let's first of all use the boundary condition only, and then we'll convert the tilde thing into the r bar thing. Okay. So what is the first boundary condition? The first boundary condition says that u hat at r bar equals to 1 is 0, which means if u hat at r bar equal to 1 is 0, and we know u hat is uc plus up, and up is just a constant, which means this will mean that this will mean that uc, okay, uc hat at r bar equals to 1 would just be 0. Okay, this is the first boundary condition, and the second boundary condition is that the modulus of uc when r is basically 0 is less than infinity, which is the finiteness, or the other way of telling that du hat by dr, okay, this would be tilde basically, du c hat by dr tilde is 0. Okay, now if we use this boundary condition, you will see that whenever this r tilde goes, so whenever this r tilde approaches 0, the modified Bessel function of the second kind approaches infinity. Okay, this is something that you can see. Okay, you can just plot Bessel function in the internet or in MATLAB or wherever you wish, and you will see that when the independent variable goes to 0, the Bessel function of the second kind, or the modified Bessel function of the second kind, approaches to infinity. If that is the scenario, what should be the value of b1 in order to satisfy this boundary condition? Can you tell me?
0.
Exactly. So because of this finiteness boundary condition, b1 has to be equals to 0. All right. Then the only task is to just calculate this a1, and let's now use this. Okay, let's now use this. Just 1 second. Okay. So yeah, so this means b1 is 0, but now we have, so just 1 second. You cannot directly write this in terms of uc, because u hat is basically uc plus up, right? And this in turn, when r tilde becomes equal to 1 is 0. So we will use this boundary condition afterwards, because there is a summation of these two terms here. I forgot that. Sorry for that. But before like evaluating a1, let's now do the conversion to r bar. So if b1 is 0, what we will get is we will get uc hat as a function of r tilde is basically what? It is a1, and we will find out a1 shortly, times j0 of j0 of what is j0 of r tilde. And we know that r tilde is what? It is r bar alpha root I, right? So it is a1 j0 of r bar alpha root over I. I think so far there is no confusion here. Okay. So this means we have evaluated the complementary function as this. Okay. Anyways, just this. Leave it. All right. So what should be? So if this is the case, what is then u hat of r bar? So this is the bar, because we did the change of variable here. So what is u hat of r bar? It is just uc hat of r bar plus up hat of r bar, right? And uc hat is what? Uc hat is a1 times j0 of r bar alpha root over I plus what is up hat? Up hat is just this, right? It is, so it is just this. It is 1 by I alpha squared, okay? It is just, so it is just 1 by I alpha squared, and this is u hat of r bar. Now we will apply the boundary condition, the second boundary condition, that is the no slip boundary condition. So the no slip boundary condition says that, so the no slip says that u hat at r bar equals to 0 is 0, which means, see, you cannot apply this into the complementary function, which we did here. That is simply because this is the boundary condition of the entire solution, right? You cannot simplify this to the boundary condition of the complementary function, saying that uc at r bar equal to 0 is 0. This is not possible because the entire solution is a summation of the complementary function and the particular integral. And that's why we have first summed up the solution and then applied the no slip boundary condition. Okay. So the no slip
How
boundary
so
condition.
this
Yeah. Yeah. Tell me.
R bar equal to 1, right? No slip condition.
Yes, r bar equal to 1. Yeah. Yes. Thank you. Thank you. Is r bar equals to 1. Yeah. So did I write 0 somewhere? Yeah. This should be r tilde equals to. So when r bar is 1, so yeah. So this becomes equals to 0. But this, so the better way is that let's not write this boundary condition in terms of r tilde. Let's use the second boundary condition and then use the first boundary condition. Then I don't think there would be any like ambiguities here. Okay. I hope this is clear. So we have used the boundary condition, that is the second boundary condition r tilde. That is possible because we know that even if we are doing a change of variable, which is basically of this form, okay, which is basically, where is this? Which is basically of this form, still the modified Bessel function of the second kind goes to infinity. And we know that our solution cannot go to infinity. And the only way that is possible is that the coefficient has to be equals to 0. Okay. And then we use this no slip boundary condition now, which is basically no slip boundary condition. Okay, so let's do this. So this means what? This means that a1 j0, okay, of alpha root over I plus 1 by I alpha squared is basically equals to 0, which means that what? This means that a1 times j0 of alpha root over I is equal to minus 1 by I alpha squared. And what do we get? So we get a1. So we get a1 as, I hope the math is clear. So we get a1 as minus 1 by I alpha squared j0 of alpha root over I. Okay. So we got a1 basically. So we got b1 and we got a1. Yeah. So once we know a1 and b1, we just need to substitute it into the governing equation, into the main governing equation, which is what? Which is basically this. Okay, which is basically this. Okay. So what was our main governing equation? That is the main equation on UC hat. So UC hat, or just 1 second. Just 1 second, guys. Okay, so okay, let's, yeah. So what was UC hat basically? So UC hat was A1 times it was J0 of, so it was J0 of R bar, R tilde, sorry, and R tilde is R times alpha root over I. It is J0 of R times alpha root over I plus B1, and B1 is of course 0, so that we know. So this becomes what? So if I substitute A1 here, it becomes minus J0 of R times alpha root over I by I alpha squared times J0 of alpha root over I. This was the complementary function. Okay. Of course, these will be R bars. Okay. And what was the particular integral? So the particular integral was, what was that? So it was 1 by I alpha squared. It is 1 by I alpha squared. Okay. So if this is done, then we are done. So this means what is u cap of R bar then? So u cap of R bar is just the summation of these two things. So u cap of R bar is just UC plus UP. So if you just do this, it will become what? It will become minus j0, okay, times r bar alpha root over I by I alpha squared j0 of alpha root over I, okay, plus up, which is 1 by I alpha squared. So if you simplify, if you simplify this, then u hat of r bar is just, so if you simplify by taking what, 1 by I alpha squared common, then you will just end up getting 1 minus j0 of r bar alpha root over I by j0 of alpha root over I. That's it, guys. So we now have a complete solution of u hat of r, and that is sufficient to know how the velocity profile looks like. Why? Because the total solution is nothing but u hat of r multiplied by e power I omega t. So let's name this, let's name the equation. We had got a lot of equations here. Let's name it as equation 6 maybe. Let's name it as equation 6. So the total solution, that is, sorry, that is u, which is a function of r bar and t bar, is basically what? It is just real part of u hat of r bar e power I t bar. Okay, where u hat of r bar, where this u hat of r bar is given by this equation. Okay, so that's it. That's the solution that we are basically looking for. Okay. Right. I understand the math is little bit absorbed here. It's little bit more mathematics. But yeah, so that's how we, so if you want to get analytical solutions of PDE, you expect this kind of mathematics to pop up at least in your analysis. Okay. All right. So I'll stop here for some time, and basically we'll just do this. So before that, can you tell me how, so is this solution dimensional or non-dimensional? Can you tell me?
Non-dimensional.
So how do we get the dimensional form then? Because ultimately someone might ask me, right? Give me in terms of the properties. How do we
Alpha
get?
will
Exactly. So we'll expand alpha there, and then this we will
be
write it
bar.
as, so this, yes, this non-dimensional we'll write it now as the dimensional divided by the characteristic, and we know what characteristic look like, right? It is some g naught times r by mu square or something like this. Okay.
Yep.
Just substitute this and you will get the non-dimensional. You will get the dimensional expression. Okay. So this is the essence, basically this is the essence. See, now as I told you, my entire solution depends on just one quantity, that is the Reynolds number. Okay, if I tune the Reynolds number, I basically get different velocity fields. Okay, I don't need to individually bother about the viscosity, the density, and so the omega or so on and so forth. Okay, what I will do is I'll just tune the Reynolds number, which obviously is, so the properties are essentially embedded into this Reynolds number, but I don't need to think about that individually. And that's why this is the beauty of solving problems non-dimensionally. Okay. So I'll stop here for some time. You can basically plot this in MATLAB. If we use something which is known as, so in MATLAB, just search modified Bessel function, basically, and then you will see that you just need to give the input. So all you need to do is just define the function. So you just need to define this thing. You just need to define this thing. Okay, and just need to specify what is the order of it, and then in MATLAB will just basically plot you that argument into that. So it will just plot. So you just need to define this argument. Then MATLAB will basically give you the modified Bessel function of this form. Okay, so you can plot this in MATLAB basically and try to get an essence of the velocity profile. Maybe you can plot it as a function of alpha. See when alpha, so you can put alpha equal to 0.1, or you can vary alpha from 0.1 to 10 maybe, and check how the velocity profile look like. If I get time, maybe I can show this in the next class or in the next week interactive session, how the velocity profile essentially look like. Okay. All right. So so I'll stop here for today. If you have any doubts, you can let me know. In the next class, I will again recapitulate what we did in this class, and then we'll begin basically into looking some 2D problems, and we will see. Yeah. Okay. If you don't have any doubts, thank you very much for attending this session. This session again will be,
One
yeah,
doubt can
yeah,
I ask?
yeah, sure.
Yeah. This is like a PD with one. We should use one initial time condition and two boundary condition, right?
Correct, correct. In principle, see, that is a good question. That's a very good question. So what? So I'll repeat the question. What Ayushi said now, that since we are essentially we are essentially where it is. Since we are essentially solving a PDE, which is both a function of time and R, in this solution, we just use two boundary condition without using any initial condition. And I said that the solution is something like this. Okay. But here, so the catch here is that since we know that a solution will already be a time periodic solution, we are not essentially solving for t. Okay. We know that t will just oscillate in time. So time here will just appear as a parameter. Okay. It will not appear as a variable. It will just appear as a parameter. So the prime essence of so the primary variable that we will solve for is that r actually. Okay, and once we know the function of r, the complete function is just going to be that function of r multiplied by e power I omega t. Okay, so this is,
Yeah, and
yeah, yeah.
in case we don't have
Hmm.
this periodic boundary
Then yeah,
condition.
then you need to use the initial condition as well. Then you need the initial condition as well. That is true.
Yeah.
So there will
Okay.
be one more constant, and in order to get that one more constant, you need to use initial condition. That's it.
Okay.
All right. So if I correctly remember, in Stokes' second problem also, you don't use the initial condition if you remember. Okay, you just use the boundary condition.
Yeah.
I-
Yeah.
Correct, right? Yeah. So that's the essence. Okay, but that's a very good question actually. Thank you for putting it forward. I hope this is clear. All right. If no other questions, uh, I would stop this session here. Thank you for joining, and we will meet in the same time next week. Thank you, guys.
Thank you.
Yeah. So I'm ending the meeting.